Okay, welcome to my talk. So the title of my talk is which machine learning models are least wrong and which ones are not even wrong, deep questions here and there. So part of my talk is meant actually to raise questions rather than to answer them. Having gone into applications recently and being not only a data scientist but a medical doctor, and seeing recently how these areas start to interact, I've been thinking a little bit about scientific standards in what is called big data, the field of big data, or scientific standards in the empirical sciences, or more specifically, say, in evidence-based medicine. So I've been, thinking a little bit what makes data science proper science and where are interesting things or issues that we might need to think about as data scientists or, say, as the Alan Turing Institute. So science, what is science? Well, data is often defined as information that is measured systematically or codified in some way. So data science as a science is an empirical science, as long as data are concerned. So good data science should actually be good empirical science in the sense of the above, and vice versa. Actually, in empirical sciences, something is measured, which is the definition of data. So actually, this is a quite general question. If we are dealing with data, what are the proper scientific ways to do so? Right, so instead of starting with good science, right, I'm starting with a very superficial way of seeing bad science. Right, so medicine has seen actually a lot of bad science across the ages. So, for example, if you go to a quack doctor and ask them for a cure of your disease, they may recommend something, and it may work or if it may not work. And if it doesn't work, well, you maybe didn't believe enough in the cure, right? So how do we know that a suggested cure is good? Or in modern ages, you go to the data analyst, ask them for an analysis, and then something comes out of it, right? I mean, a bad analyst might suggest, say, a specific model without any reason, and if it doesn't work in the end, if the machine breaks, if the patient starts to die when the model is applied in practice, then maybe you didn't tune the model right, or maybe you didn't apply it correctly. But what are actually guiding standards that one should follow? How can one separate the good from the bad? And doing a little bit of consulting myself and medical applications, I've compiled a very subjective map of buzzwords that might or might not be used. Of course, the most frequently used buzzwords are also quite successful in the sense that pseudoscientists use them in order to legitimize bad science, even though these words can mean perfectly valid scientific approaches to data. So the situation is not that easy. So it's not the use of a certain word that makes science good, or the non-use of certain words, but what is good science? Right, so the scientific method, you might have heard about it in school. It's about observing nature, which in data science would be acquisition of data, making a hypothesis that can lead to a testable prediction that you can test by carrying out an experiment. And the experiment can provide evidence in favor of the hypothesis by agreeing with the prediction that one has made, or by being in disagreement, which would be evidence against the hypothesis that led to the prediction. And of course, the process is repeated. So the scientific method applied to data science may be the two most important statements about this I would like to mention, how have already appeared in the title of my talk. So pseudoscience may actually be characterized in a certain way by a saying of Wolfgang Pauli, by not being even wrong, or by not even being wrong, meaning that claims are made that are not testable. So if they are not testable, they are not amenable to falsification or verification, hence they don't pertain to the empirical nature of reality. And of course, there's other characteristics of pseudoscience, like using actually scientific terminology, even though the argument is not scientific in the sense that there is no experiment, but the argument is the important bit, not the scientific terminology, not the use of formulae, or not actually what you do inside your computer with the data. So whether you're using a statistical software suite, whether you're using the right statistical models, it is not science unless it follows the scientific method. So if a claim is not wrong, when is it right? Well, following a famous claim of George Box, actually all models are wrong, since all are necessarily approximations to reality. All models are inaccurate, but that doesn't mean that modeling is a moot task per se, but instead of seeking the one true model, there is models that are differently good for particular application scenarios, and what quantifies good might depend on the scenario, but one should generally follow some quantitative version of Occam's razor here, which, if you read the context of the sentence in which all models are wrong is said, is more or less paraphrasing it correctly, I would hope. Right, but what does it mean? What does it mean for a model to not be wrong? Well, if you are in the real world, you are interested in certain types of applications. So here are 3 stylized applications I've encountered, and which may cover broadly what data science, or where data science is currently going. So for example, if you're a medical doctor, you're actually interested in finding the best therapy for patients. So maybe a big data model is the one that suggests the best therapy, right? But of course, then you need to be sure by medical standards that this suggestion is actually sensible. Or maybe you're a retailer and you want to minimize customer churn, and maybe the strategy to avoid customer churn is suggested by a big data model. So again, the same question: what is good? How do you measure that it's good? Or you're manufacturing some kind of products, you have a manufacturing chain to optimize parameters that influence, say, the quality of the product. Then how do you optimize that? Again, the same question. If you now want to employ data scientific or big data type of techniques, well, how do you know? What is, of course, of interest is an applicable solution. So it's a solid, quantitative, interpretable, deployable, in one word, practically useful answer to the scientific question that comes from the domain. What's not necessarily of interest, what algorithm you employ, as long as you have, well, accuracy, interpretability, deployability, and so on. So in a practical application scenario, what this actually says, the goodness, the scientific appropriateness of data science is measured by the scientific question it solves, so from the context it is employed in. Being inspired a little bit by the usual criteria that medical doctors have come up with in the evidence-based medicine revolution, or based on criteria that are also generally employed to characterize good science. So one very important bit is reproducibility. So if someone claims a method is good for some purpose, then you actually want to be able to check it, right? Because if the quack doctor claims that the medicine will work, then how can you tell except that someone has tried it out before? Right? And furthermore, that it is also known how you would have to try it out again, how to make sure it really works if you want to check it for yourself, instead of just believing a random statement here. Right? Then furthermore, the problem is about dealing with some data. Right? So the data, as it was collected, as it is available, it needs to be itself valid. So the data needs to be in a state that allows to make statement about the data itself, so that there is not too many errors for the data set to be useless. Furthermore, you want to make some generalization. So often you want to use a data set to say, well, the treatment is not only good for the patients in my hospital, the treatment is not only good for customers in one specific location, but it is generally a good idea to apply this therapy if you have this kind of disease. It's generally good if you have this kind of manufacturing process to apply this kind of modeling strategy. Right, so external validity needs to be guaranteed somehow, and of course, also important, there needs to be a quantitative measure of how good the task was solved, of how good, whatever the scientific question was, whatever the experiment was, there needs to be a place where the experiment can say, yes, it worked, or no, it didn't work. And that ought to be quantitative, otherwise it will be subjective and subject to personal opinion, which is, well, not good. Speaking of solving a specific task, so my talk, as I'm also a machine learner by formation, so in the big data realm, there is specific tasks that machine learners or statisticians often look at or use models for, which are called slightly differently by community, but in essence, these are mainly the so-called supervised and unsupervised learning tasks. So I'm going to briefly explain it. If you're familiar with machine learning, then you will know these. So in supervised learning, you have some data that comes with a label that should be inferred from features in the application. So in this example application, you have measured yellowness and roundness of certain objects, and then in the actual application, you want to infer what the object is given the features you measure. For example, in the famous example of image recognition, you might have a pixel image, so a pixel, for example, a grayscale values per pixel or color values per pixel of an image, and you want to actually assign the label of what is on the image or who is on the image if it, say, comes from a surveillance camera. Right, so this is called supervised learning. Classification and regression are subtasks where the label is of a certain class or it's a natural number. Models we have heard about that do this, for example, support vector machines, neural networks, and so on. Right, so this is labeling data given examples of the same kind that have been observed before. Then there is unsupervised learning where the data doesn't come with the labeling. So you have some kind of data features or variables observed, but you don't actually know what you're looking for. So maybe you want to look for a specific structure and a pattern, and then a smart method would say, well, maybe these data points all lie on a plane. Maybe these data points are, yeah, a cat or something. Clustering and the dimension reduction are subtasks. And again, models you might have heard of is maybe principal component analysis for dimension reduction, k-means for clustering, and so on. So in unsupervised learning, you don't actually have a label, and the method produces you some interpretation of the data that you have. Now, how do we check a model that does any of these tasks is any good? So first and foremost, you don't know whether the model is good, right? So there's no model that you can assume to be good for all data. Otherwise, the concept of model wouldn't make any sense. Right? For a given data set, you don't know which model is going to be best, so you need to find that out, and you need to quantify that in an experiment that is actually model independent. Because if you're interested in the application and not in the model, then you need to check, and you need to check quantitatively by what we have seen about the scientific method. So in machine learning, there are certain ways to do that. I will explain how this is done for supervised models, and that's relatively standard, so that can be found in most machine learning books how this is done. So if you have a prediction strategy that learns a model from training data and uses this model to predict the labels on new data, right, then the so-called validation on an independent test set strategy is you simply take the data set you have, you split it in training data and test data randomly. So by the randomness, you ensure that the training and test data are of similar kind, and you don't feed the labels on the test set to the machine. You compare the predictions the strategy had made with the actual labels, and from this comparison, you obtain quantifiers of prediction goodness. Multiple methods are compared in the same way. So multiple methods are subject to this whole procedure, and then you can statistically compare. So what is important, actually, well, one thing is that this is, to my knowledge, the only way to test external validity of models without using any knowledge about the particular model in the validation. One restriction or limitation of this is that you only get external validity guarantees if any new data is guaranteed to come from the same process as the test and the training data, so that these are representative. So mathematically, they usually assume to come statistically IID from the same sampling process. Back to science. So where is the experiment? Where is the ground truth? So in fact, we do make a prediction, but that is not in itself, the prediction of the label is not the scientific prediction. The prediction actually is that the model will predict well. And the ground truth are actually the test labels here. So we can check whether the model predicts well by comparing the predicted labels to the held out labels. And the quantification is the quantitative measure of model goodness in the supervised learning setting. So actually, this is a closed scientific loop, and the ground truth is there in supervised learning. Crucial point is there needs to be some moment in the whole experiment where it can turn out that the model is not better than, say, alternatives, baselines, right? So you need to quantify somehow whether the model is better than a random or uninformed guess. Otherwise, if you do that wrong, otherwise it's not scientific, it's pseudo-science. So if you just want to hear about some ways to avoid being wrong by being not even wrong, some popular ways, right? So don't compare. If you don't compare, then right, nobody will notice that you're wrong. Or if you compute only the goodness of your method for one method, then it's the same because there's no comparison. Or if you forget to compare to baselines, right, that's also a good way to avoid making an experiment that could tell your model to be wrong. Or if you compare only to a model which is even worse, or if you forget to actually quantify the comparison to get a yes or no answer in any statistical sense. So it doesn't need to be frequentist, it can be Bayesian, but some quantifier ought to be there. Otherwise, this is pseudoscience, even in the supervised setting. But how to do this properly actually is an interesting question that not a lot of people are looking at, but that is actually of enormous relevance in practice. So speaking about modeling that is not predictive or supervised, well, that's also interesting to think about. So unsupervised learning. So the model, so if you do it in the worst possible way, then what the process will produce is some kind of picture, which is the result of the analysis. So it may be a nice accumulation of clusters, it may be bars or something, or it may be some numbers, formulae even, which is the end of the unsupervised analysis. So is that scientific? Is it wrong? Or actually it's not even wrong if that's where you end the application of an unsupervised method, right? Where is the ground truth here? What do you compare it to? What is the experiment? And even if you claim to say, well, you see something in the picture, that's not better than reading entrails if you do not have any good reason to say so, right? Or saying, well, there is actually no goal. Well, if there is no goal, if there is no criterion to check, then why are you doing that? Interestingly, Sometimes you find in Bayesian methodology similar kinds of argumentation. So just to the end of the end result is some posterior, which might be a predictive posterior or a posterior of parameters of a model. So look at the posterior, it is beautiful. Hence we are done, are we not? But again, what does it even mean? Or if you say you don't want to quantify, but you ought to quantify, otherwise how can you say that an experiment had failed? So you don't need to apply a frequentist hypothesis test. You can do a credibility analysis on a Bayes factor, say something which is Bayesian, so that's fine, but you should quantify. Otherwise, this is pseudo-science. Or one interesting statement that you hear often said by Bayesians or frequentists that these are actually incomparable approaches, but actually they claim to solve the same type of problems in real life. So how can you make such a statement if the problems they're actually claiming to solve are the same? Well, this reminds me as a doctor of some alternative quacks saying, well, these are completely different approaches. You cannot compare, you cannot measure, right? But actually, unsupervised learning and Bayesian statistics, of course, is not pseudoscience, is done properly. So the two main ways, of course, this is up to discussion. And again, I find it interesting to think about it, how this is done properly within the complete data analytics workflow. Well, so for unsupervised, often you find it combined with a supervised method, and you can do it in the way I've outlined for supervised methods. Or you actually can turn it into a probabilistic model and, say, consider a predictive likelihood or a Bayesian corrected type likelihood, predictive one, as a check, or as a quantitative check for your model. So whether this is now unsupervised as long as it's probabilistic, or whether it's Bayesian or even probabilistic programming, that's one way to validate models externally and ensure external validity, actually. But interesting question for scientists and practitioners. What would be the right way where you can, say, use Bayesian and frequentist models alike to solve the tasks? Speaking of tasks, there's a couple of advanced ones as well that I should also mention. So complications might arise in the labeling. So you might have a non-explicit labels like in reinforcement learning. There might be effects of time, so data is revealed over time. You might want to forecast a new data point in the future. You might want to actually say something about a data set which is different, say patients, a cohort at a different hospital from the one you did your analysis on. And the problem here actually is this generalizability assumption does not statistically hold. So one interesting point, there are to no model agnostic guarantees of external validity as soon as you have correlation or a difference between your test data and your new data if you are not careful. So without any further assumptions, you lose model agnostic external validity. So that has actually important practical consequences, as such models that are fitted or learned in a slowly changing environment may completely break once that environment suddenly starts to rapidly change and move. With this, coming back to the real world, so how do we put science into data science properly when we're interested in any of the applications I've mentioned? Say, the medical one, which is very, very relevant these days, actually, in the context of big data science. So if you do a medical trial, right, what do? So you claim a treatment is good for a disease, right? So the observation might be that if you give the treatment, then people have a better outcome than people who have been administered one of the baselines. And causality is inferred by ruling out other possible causes, so that actually the improvement in outcome is due to the treatment, right? So ruling out randomness is done by quantification. Because if the difference could arise plausibly just from randomness, then you cannot attribute it to the therapy, right? You need to use the best baselines possible. You need to rule out systematic errors, characteristics of your data set, And of course, there's always, because this is an application that affects the real life of real people, ethical considerations that are to be taken seriously in such a context. Whereas, if I can show you a stylized and maybe a bit humoristically overtuned comparison to big data science, as in data pseudo-science, right? So randomness, well, the data are big enough, you don't need to test. As a baseline, you come up with them yourself, right? That's what you do, isn't it? Systematic errors, well, there's no confounding or publication bias in machine learning, is there? Everyone uses the 3 data sets that were there since the beginning of the time, hence things are valid. And anyway, everything is better since the models are fancy, right? Obviously. So thinking of this, and I'm coming to an end now, right? So what would be proper levels of evidence when it comes to data science applied to practical applications? This is actually something I believe we as scientists should be thinking about, and we as the Alan Turing Institute should also be discussing, right? So if the model is to be applied, well, having observed usefulness of the model in an interventional context is actually of higher evidence value than just having the model run, say, in a split data regime on a data set sampled in one hospital, for example. So if you want to say, oh, the neural network recommends the right therapy, what would I have to actually do to confirm evidence that this is actually useful and it doesn't kill people, right? And, well, inspired by these medical hierarchies of evidence, right? So if you put actually a lot of claims of machine learning models to test, then at least as regards my knowledge, I wasn't able to find a lot of evidence for the first level. I mean, even if it comes to neural networks, right, they're usually applied to the data sets everyone uses. So how are they useful in a practical interventional setting, in a hospital, say? Who knows, right? Neural networks applied for anything else, where are the meta studies, right? IBM Watson or cognitive computing, you might have heard about it. And it's going to be applied in hospitals. Is there any evidence for that I am unaware of? Is there any comparison studies on machine learning methods applied to any types of data, or even general data sets that you might find in these repositories? I mean, there's one study by Delgado which tried to do that, but actually they tuned on the test set, which biases the whole study. So, and as said, for the more complicated modeling tasks, we don't even know how to check whether they are wrong or externally valid properly, which is a lack in theory. So instead of asking for questions, I'm asking questions first, which might be interesting actually to discuss, since I don't know the answer either. So if we are asked how one should start exploring data science, by a company, by a hospital, by a government agency, what do we answer? Which models are state of art for a specific application? What do we answer? And what are the limitations? How do we even determine the limitations of a model in a practical application, right? And of course, these 3 are not the answers we want to give, even though the first one is justified because the Alan Turing Institute really started working on this since recently. But well, what can we say? So just want to mention the OpenML project, which attempts to give a proper basis, a infrastructure for comparisons as such. But there's also theoretical gaps which, in my opinion, need to be filled, and which I think it's also mathematically appealing to work on.